Today's class is on, we're already in chapter 18, which is principle of work energy, conservation of energy applied to rigid bodies. Okay, so we'll basically do the same things which we did for particles, but now we have rigid bodies. So I'll give an overview of important formulas and we'll start with problems. Okay, so in chapter 16, we've seen that, sorry, chapter 17, we've seen that there can be pure translation, or there could be rotation about a fixed axis, or there could be a general planar motion, right, where you do not have a particular axis of rotation. So each of these cases, we can find the kinetic energy for pure translation. The kinetic energy is half mass times the velocity of the center of mass squared. Okay, this is that the rigid body is just moving in either the xy direction or the tn direction or r theta direction. There is no rotation, so there is no inertia coming on the equations. The second case is rotation about fixed axis, such as a pendulum, right? So rigid body, center of mass, it's rotating about an axis. So this is the point O, this is G. So it's rotating about the axis O. So in this case, the kinetic energy is either get it as half mvg square plus half ig omega square, or if you knew the inertia about the axis of rotation, which is IO, then you could just write it as half IO omega square. Both these are valid formulas. Finally, we have general planar motion. What's that? Yes, you missed it. I had 5 questions today. 5 questions? I'm just kidding. I did no questions today. Oh, sorry. Oh, don't worry about it. It's rainy and it's slow today. So if it's general planar motion, for example, a disk rolling or disk slipping, then the total energy is half m vg square plus half ig omega square. Okay, and it's important to note that you cannot write this as, do not write this as half I0 omega square, because there is no axis about which the the rigid body is rotating. So do not do this. It's a very common mistake. Don't write it this way. So it's key to first figure out if the problem fits in which category and then use the equation. Now, what I can tell you is that this particular equation, the last one, is the general motion. It is a generic case, and those two equations, 1 and 2, are special cases of the equation 3. So for example, if there's only translation, then there is no rotation, which means omega is 0. So you'll be left with half mv square. If there is rotation about a fixed axis, then you can see that the formula is the same as the first one in the case for fixed axis. So it's always best to use the last formula and reason out backwards to see which formula it fits under. Okay, so work of force, and I'll be done with everything I need to do to get started with problems. So work of force and work of moment. So the definition of work done is F dot dr, where F and R is a vector. So work due to gravity, as we've seen in the chapter on particles, is always minus mg delta y, where we know that it's upwards. If the particle is moving upwards, then force is downwards, y is upwards, so it's going to be negative, and if it's downward, it's positive, right? This is the sign. Then there's work done, work due to spring. I'll write it at that as US, and we've seen that that's always minus half k times the stretch in the spring. And the new thing here is work due to a moment. For a particle, there is no moment because there's no rotation really. Well, it's in translation. But for a rigid body, there can be rotation. And for example, there could be a motor which is subject to a torque, because of which there is work done by the motor, and that is given by m d theta. Okay, where m is clearly the moment which is sticking out of the plane of the paper. Because we are doing only two-dimensional motion, the moment is always in the k direction, so I did not quite write it as a vector, and d theta is the rotation which is in plane. Okay, any questions on this? Okay, so let's just put everything what I just discussed in some problems. Yeah.
The rotation about a fixed axis in a planar motion is the same formula, except for IO omega squared.
Wait, you're saying case 2 and what?
The formula for rotation about a fixed axis in general plane use the same formula.
Yes, that's right. It's the same formula, absolutely. What happens is, okay, maybe I should just show it to you. So the formula is the same because general planar rotation about fixed axis is a special case of general planar motion. Okay, what you will do, for example, a pendulum is an example of fixed axis. So, for example, what's easiest actually in this problem is to use this formula. This is the easiest thing to do.
That's when you know a point about which
it rotates. Yeah, you can see that happening if you put v equals omega r, right? If this is r, then it turns out that this formula T will give you I g plus m r square omega square. So if you put this in, if you put v equals omega r, vg equals omega r, then you should get T equals Ig plus mr square omega square, and that is, sorry, half that, and that is the same as half I0 omega square. So you actually can derive the equation from the first one. Okay. Any other questions? Okay, so let's use this things on a few problems. So first question, the disk which has a mass of 20 kilograms, so 20 kilograms is subjected to a couple moment of m equals 2 theta plus 4 Newton meters, where theta is in radians. If it starts from rest, okay, so initial angular velocity is 0. Determine its angular velocity when it has made 2 revolutions. So theta initial is 0, theta final is 2 revolutions. So 2 revs is so 2 revolutions means that it completes 360 and 360 or 720 degrees. But we need to write that in radians. So what's the revolution? It's 360 degrees. What's 360 degrees in radians? It's 2 pi. So it's 4 pi. Okay, so there's a disk. Clearly, because there's a moment, it starts spinning faster and faster because the moment is positive. Well, it's negative by the sign convention, but it's going to spin the disk clockwise direction. Some point of time, it reaches an angle of 4 pi. We got to find the work done. No, determine angular velocity. Sorry, omega f. Okay, so clearly m does work, and that's why the angular velocity has increased from 0 to omega f. Okay, so here's something I recommend: always draw free body diagram, because we always give you credit for free body diagrams. It is not okay to draw a free body diagram like this. This is not a free body diagram because the body is not free there. You're just showing the forces, it's not free. You cannot show OX and OY when it's already connected to the pin joint. A free body diagram is when you pull things apart, when you pull a body from its constant. You could draw a free body diagram of, in some cases you draw a free body diagram of multiple objects, okay? But that's a free body diagram of the system. In this case, you have to pull this thing out, which means you got to draw this separately like this. OY, OX. Okay, gravity is not given. It doesn't matter. I can put gravity if I want and then show mg. Okay, this is, if it's in the vertical plane, yes, there's gravity. If it's in the horizontal plane, spinning this way, there's no gravity. But you see that it doesn't really matter. Gravity is not going to be a factor in our computation. Okay, now coming to solving it, now what I can tell you is that when you see a problem like this, you can always do all these problems which involves forces using F equals ma. Okay? If you use F equals ma, you should be able to solve it. So you do not need to know anything about this chapter to solve this problem. So I will write this as method 1, which is you can take moments about point O and say that moment is, this is a case when there is rotation about a fixed axis. So it is I-O alpha. And then you'll write the moment about O. You can find the inertia of a disk. Inertia disk is m r square. So you can find the inertia about O, which is going to be mr square. My bad, it's divided by 2. And then you can find alpha, which will be a function of theta, and then integrate that once to solve for omega. Okay, that's one way to do it. What happens is when you use the conservation of energy or work done, you do not have to integrate. That's the advantage of using the principle of conservation or work done, principle of work done. Okay, so I'm going to use what we're doing in this chapter, which is method. So try this. So method 2 is figuring out the work done. So the formula is, and this is from the chapter on particles, T1 is the kinetic energy 1 plus the work done should be equal to the kinetic energy after all the work is done. So when do you apply this? Well, whenever you're asked to find velocity as a function of distance, that's when you use the principle of work energy. Because what does the principle of work energy have? It has energy, so velocity, and it has work done, which is typically a function of theta or s. So let's try to use this principle. T1 is the initial energy of the system, and that is what? 0. T2 is the final energy of the system, right? I mean the kinetic energy of the system. It's going to be I-O omega squared, because this is rotation about axis O. Okay, so that is half m. It turns out that the inertia about O is the same as inertia about the center of mass, which I'm going to assume, by the way, is at the center, because it's a uniform disk, times omega square. Okay, and the final thing is the work done. So the work done due to moment m is m d theta. M is 2 theta plus 4. That's m d theta, and then theta goes from 0 all the way to 2 pi. No, sorry, my bad, 4 pi. Okay, so if you put the values 4 pi and 0, you integrate that, you get 208.18, and that is in the units of work done, Newton meter, that's Newton meters. Work done is force times distance, so Newton times meter, yeah. You could put joules or joules, same as, it's the same. Joule is 1 Newton meter. So putting back in the equation, we have 0 plus 208.18 equals half mass is 20, the radius is 0.3 square times omega final square. So omega f comes out to be 21.5 radians per second. I can just write this down and you can check me on this. The moment about O is going to be m d theta. I-O is mr squared divided by 2, and alpha, since I want to find alpha as a function of theta, I'll use this formula. Sorry, my bad. This should be m negative. The moment is m, right? About O. So yeah, if you integrate this equation, you should get this, and then you can integrate this from 0 to 4 pi. Okay, my claim is that when you integrate this, you'll get exactly this value. It's the same answer. Okay. Any questions? Okay, here is a slightly harder problem. So the center of the thin ring of mass m is given an angular velocity of omega 0. If the ring rolls without slipping, determine its angular velocity after it has traveled a distance of s down the plane. Okay, so that's the omega 0 is the initial speed.
And there were something as S down the plane, do they mean along the length of the hypotenuse or just like it's changing y direction?
It's exactly the way it is shown, so it's along the plane. So what it means is that the point O has moved a distance of s. So the center of mass has moved a distance of s. So we're given m, omega 0. We need to find the final angular speed, and we also told the distance traveled by the ring. Okay, so as I said, always draw free body diagram. Okay, is that it? I should always put a friction for rolling. Okay, so that's it. Now, again, the question is how should I solve this? I could potentially solve it using F equals ma. Okay, if you do that, you should get the same answer which I'll get using conservation of energy. In general, I said conservation of energy or work done is a trick you use when you're trying to find omega v as a function of s or omega is a function of theta. You should use work done or conservation of energy. Okay, we're going to see conservation of energy problems a little later in this section, but it makes your life easy if you use these principles when you're told to find v as a function of theta. But always true that F equals ma and moment equals ig alpha plus rg, the point moment about whichever point cross mag always works.
Do you know if there's, how do we know there's friction even though it doesn't mention any kind of like value?
If there's no friction, then this will not be able to roll. Friction is necessary. Friction prevents point O from slipping, from the point of contact from slipping. So if you see a problem like this, uh, you can always solve it using F equals ma, always. However, you want to use other principles to make your life easy. It's much easier to solve it that way. So this will come up in not in your next exam, which is a final term exam, but in the finals where you see a problem and you would have no clue where that question has come from, right? Because we're not going to tell you use this equation. So that's where you have to make the judicious choice of which formula to use, and that's where you will have to think about what formula to write. So this is something to remember, and you see this thing coming again and again in all questions in this problem, in all questions in this particular chapter. You will always be asked to find velocity as a function of distance, usually, and then they might ask you to find forces. So if you are asked to find forces, you are stuck with F equals ma. That is, you can use the conservation of energy and F equals ma. So the next question actually is about a mixture of the two. Okay, so let's use the principle. So again, as I said, method 1, use F equals ma and the moment equation. The method 2 is what I'll use here, is principle of work and energy. So that says T1 plus U12 equals T2. Okay, so let's try to find the kinetic energy. So I said that the generic form for energy is half mvg square plus half ig omega square, right? This is not a case where there's pure translation. There's rotation too. So it's not the first case. This is not a case where there's rotation about a fixed axis, because there's no real axis, right? So it's not rotation about fixed axis. So this is falls in the category of planar motion. So that's the formula which I'll use. I can do a little bit of simplification. Since it's rolling, the ring is rolling, I can put Vg is equal to omega times r, small r. So put 2 in 1, I get omega r square plus half Ig for a disk is mr square. Let me just keep it as it is and then sub it later on. Ig omega square. That is going to give me half Ig plus mr square omega square. Okay, so the initial energy, kinetic energy, is half Ig plus mr square times the initial angular speed, which is omega 0. The final kinetic energy T2 is going to be half Ig plus mr square omega f square. Okay, that's an unknown. Omega f is an unknown. The only thing left now is to find the work done. Okay, so what's the work done? It's the work done due to what? Gravity, right? Gravity gets this mass down. So it's not given here, unfortunately, but there is gravity. So due to gravity, what happens is, this is the center of mass. It moves down by a distance of s. So yeah, so the question is, what's the drop in height? So work done is going to be, so mg acts downwards and the displacement is downwards, so the work done is positive.
W times S sine theta.
W times s sine theta, right? H is s sine of theta. Theta is the sine then. So we are all set. We have, let me call this 3. So from 3, I'm going to put the values which I found, half Ig plus mr square omega 0 square equals half m Ig plus mr omega f square plus mgs sine theta. Okay, the inertia Ig for a disk is mr square divided by 2. So what I get effectively is Ig is mr square divided by, oh sorry, it's a ring, my bad. A ring is mr square. A disk is mr square divided by 2. So if I put it here, I get mr square omega 0 square equals mr square omega f square plus mgs sine theta. So I can get rid of m and I can solve for omega f. I think I did a mistake here. So it's t1, that's right. And then it should be plus u12. So this should be on the other side. So we'll rewrite this. So omega f is square root of omega 0 square plus gs sine theta divided by r square. Okay, any questions on this? Okay, it's very straightforward. So I would highly recommend you trying it out this way. Try this and see if you get the same answer. It'd probably be more work than what I've done in solving this problem, but it's worth trying it out.
Because as you equals m1 squared, that's why the 1/2 disappears.
The half cancels, drops off, right? So it's mr square plus mr square, you get 2, and the 2 in the numerator cancels with the 2 in the denominator. But it's going to be hard because think of it, it's a sea of questions. There's a sea of questions you're going to study for, right? And when you see a question, you've got to know where it's from and apply the principles. Now it's going to be not these formulas, it's going to be a whole lot of formulas.
So for the final, you're not gonna do like only all exams, right?
It's going to be all cumulative, everything.
But some professor tell you like for the final, just study like the last previous board exam, study this material.
Can you tell me who that professor is?
In physics, they.
Oh, in physics.
Like that.
Yeah, that's why they don't do well. We are engineers.
Not exactly the same question, but like same material.
So I think that what I've seen from talking with other instructors is that we all as a group want to test you on everything. So you will not see that we'll weight the last things more than others. You might see a little bit more questions on that, but I think you can expect to have a more uniform playing ground. And the reason is this, eventually, it's not that when you see a problem in real life, you will be told it's from chapter 16. You got to be able to look at the whole sea of questions and sea of chapter and say that this is what I need to apply, this is the principle I need to apply. So that's the whole point. So we might tell you something like we did for the last exam where we told you, expect a problem on this section. We might tell you that. Or as you saw in this exam, was pretty clear from the formula sheet on what question you would have got, right? So you can, I guess, get some hints that way. Yeah, so will probably tell you something. It's not going to be like, that's my hope. So it's just, again, not me, but all of us decide what we're going to do. Okay, so next question. The spool of mass 40 kg and radius of gyration of 0.3 meters. If the 10 kg block is released from rest, determine the distance the block must fall in order for the spool to have an angular speed of 15 radians per second. Also, what is the tension in the cord? So we need to find the tension. Okay, so always draw free body diagram. In this case, you have to, because you're asked to find the tension. So I can draw free body diagram. Where the 3 free body diagrams I can draw of the spool, of the mass, and the combined system, right? So let's draw a free body diagram of the spool. Okay, is there anything else? Well, there is the weight. Okay, now solving the problem. Well, so you're told to find the force, the tension in the cable. So clearly it means that you have to use F equals ma, because that doesn't show up in the principle of work or energy. So let's write the equations of motion. So clearly that's the equation for the mass m, and then for the spool, I take moments about point O. So this is rotation about the fixed axis, right, for the spool. So it's I O alpha. So moment about O is torque is T, the tension, times the radius, which is going to be the inner radius. So it's 0.3. That's negative, equals the inertia of the spool is half m. Okay, let me call this m1 and call this m2. So this is m1, m2, k0 square alpha. Okay, so t is an unknown. I need to find t. So what I can do is, now I have two routes. One route is, I know something about the kinematics. I know the angular speed. I need to find the distance, right? I could use the kinematics to solve for the acceleration, sub in that formula, and solve for the tension. So that's one method. The other method is to use principle of work and energy, and that's what I'll use. So method one.
So tension is not in here.
No, it's mg plus. No, but there's acceleration, right? Method one is use kinematics to solve for alpha a, and then get t. The other method, which is the one I'm going to use, is principle of work energy. So the initial energy is, kinetic energy is 0. The final energy is, now when I look at the energy, I have the choice of using the energy of one system that is the mass spool, or you can do the sum. So in this case, I do the sum because if I don't do the sum, then I'll have the tension showing up in the equation. So the energy is half I m2 ko square omega square plus half m1 v square. So the energy due to the spool is only rotational, so it's half I omega square. The energy due to the particle is only translational, so that's half mv square. U12 is the work done due to the mass falling down by a distance of s. So m1 g times s, and s is an unknown. Since the mg is downwards and s is downwards, the work done is positive. Okay. Also, we have v equals omega r, the velocity and the angular speed. The velocity of the string and the angular speed are related because there's no slipping. So, okay, it's 9:50. Give me like a minute, and I'll at least get the last part done, and the tension part I'll just post it. So 10 into 9.81 times s equals half times. So I'm trying to sub in for this. So we're given that the final velocity is 15, right? And so if you solve this, the only unknown is s. S is 5.16. Okay, then I'll just complete it how I compute tension from this. Okay, so I'll see you on Monday. Yeah.
I want to talk to you about this.